Hello, this is Ana Douglas again. Today, the seminar that we're gonna talk about it's about the computational methods in digital holographic microscopy. So the learning objective lens are we're gonna identify what is the proper reconstruction algorithm based on the optical configuration of the DHM system. For example, if the system performs in inline or slightly off axis, we're gonna get you introduced to several phase shifting DHM algorithms using 2, 3, or 4 images. We're gonna talk about how to get accurate quantitative phase imaging using an off-axis hologram and different methods to get it automatically. And we also gonna talk about if the system is working in non-telecentric routine, which are the steps, or if the hologram is placed in a position different than the image plane of the microscope, how to do the reconstruction, how to do the numerical propagation to focus the object information. So you have already heard that DHM is considered a hybrid imaging system. So what that means is that the image that gets recorded by the sensor that is not the phase imaging, it's the hologram, it's the interference pattern between the reference wave here, which is a uniform plane wave, and the object wave, which the sample is placed at the working distance of the objective lens, so that the sensor at the sensor plane, what we have is the complex amplitude distribution scattered by the sample and image by the microscope, which is composed by a non-infinity correct objective lens and a tube lens. And right, so this is my reference wave. It's completely a plane wave, which we allow to be slightly tilted, and that's gonna depend if we are in inline or slightly off axis or completely off axis. And this is what we are saying about. So if the sensor is completely at the image plane of the microscope, which is the back focal plane of the tube lens, then the object distribution is just the 2D convolution being a scale copy of the complex distribution of your sample with the Fourier transform of the pupil stop of the microscope objective lens. And the hologram, well, the sensory recording is the interference pattern. So we have here the hologram is composed by 4 terms. The first 2 terms are the intensity of the object and the intensity of the reference wave, and the other 2 terms are the cross terms, the cross product with each of the waves. So this is called the real object, and this is called the virtual image, and it's just because it's the conjugation, it's the conjugated version of the object image. So let's get it. Everything is get easily analyzed when we go to the Fourier domain. So let's do the Fourier transform of your hologram distribution, right? So if we do the Fourier transform, we're gonna see that we can assume that the hologram spectrum is composed in 3 terms. So you're gonna say, how come? So my hologram has 4 terms, but my Fourier spectrum has only 3 terms. Well, the reason that you only have 3 terms is because the first term, which is usually named as or known as the DC term, is the Fourier transform of the intensity of the object and the reference. And the reason that it's kind of like encoded in the DC term is because if you make the Fourier transform of the intensity, both of these planes of this both of these terms get placed in the middle of the Fourier domain, right? So that's what we say here, draw with this kind of like cyan circle. This is the DC term. The other 2 terms are the Fourier transform of the real image and the Fourier transform of the virtual image. Because they are conjugated, there's gonna be kind of like an inversion, so you're gonna have the spectrum of the object or the spectrum of the conjugated object, but also, because there is an interference pattern, they don't gonna get located. It's not necessarily that they're gonna get located in the same position. For example, if you are in an inline configuration, everything is gonna get placed in the middle of the Fourier domain, so you have a perfect overlay of the three terms in the Fourier transform. And ideally, if that's true, you don't gonna see any fringes in the hologram. If it's slightly off axis, then the d plus 1 and minus 1 terms are arranged symmetrically within the center of the Fourier transform, but they are placed in different positions, like first quadrant and fourth quadrant, or second and third quadrant, but it's always kind of symmetrically, and there is like a reflection. And if it's completely on the off axis, the slightly inline or the slightly off-axis configuration means that the d plus 1 and d minus 1 terms, they don't overlap together, but those terms may overlay with the dc term. And the off-axis are when the three terms are placed in completely different regions in the Fourier domain, so there is no overlay between them. So the separation between the terms is controlled by the interference angle, and there is one angle that is gonna consider like the minimum angle, where we're gonna say like alpha sub c, which is kind of like the threshold to be the system off axis or slightly off axis. Alright, so let's talk about how we need to create the numerical reconstruction, how we can decouple the object information. So this is my hologram spectrum, right? And we say that the hologram spectrum is composed by 4 terms. But the information that we want is the object image. So it's that U right here, which is completely mixed by 3 terms, but also we have here the conjugation of the reference wave. So if we go to the Fourier domain, what we care is about the spectrum of the object. And sure, it's gonna get displaced to the position where given by the interference angle, but this is our particularly what we want to get. So there are different terms, right? So let's assume that we are in inline and slightly off axis configuration. So you see, like if you have in the space domain, it's completely mixed all the terms, and if you have in the Fourier domain, they are also completely mixed. So in this particular case, we cannot do a spatial filter, because if you crop the object information, you're gonna crop the information with also the d minus 1 and dc term here, or the dc term here, so you're gonna have some distorted information. So the way of doing it is making phase shifting techniques.
So as Anna mentioned, we need to apply phase shifting techniques to recover the information of the holograms in these configurations. To do this, we can see the reference waveform as a plane waveform with an arbitrary phase offset value, in this case this parameter over here. This yields to a mathematical representation of the hologram that involves the amplitude information of the sample, but also the phase information of the sample with a constant phase offset value. So the conventional method to do this involves 4 acquisitions. This is also known as the quadrature method. In each of these acquisitions, a p divided 2 shift is introduced between them. In this case, after a bit of mathematics, we can obtain a simple mathematical expression for the complex amplitude of the object, but as we are interested in the QPI information, we can obtain, by using the inverse tangent function, the information of the phase of the sample. But of course, there are also 3-state procedures, that means methods that require 3 images. In this case, we introduce between the holograms arbitrary phase shift, but well-known phase shift. And by using these holograms, we can recover the information of the sample for simple point-wise arithmetic operation, as well as we can see in this part of the slide. Okay, what happens when we are working with a slightly off-axis recording? In this case, we need first to numerically model synthetic reference waveform, as the one that are shown in this part of the slide. And for each DHM hologram, as in any other quadrature phase shifting method, we can compensate the information of the hologram in each recorded hologram. After this, we can use simple pointwise addition operations to record the complex info of the specimen and hence the QPA data.
Alright, so far we have talked about some phase shifting techniques. I'm just gonna introduce you to new phase shifting techniques that they are kind of blind. And they are kind of getting the reconstructed phase image and the phase step minimizing a cost function. So we were saying that the hologram has 4 terms, right? That's what we are saying, the intensity of the object, the intensity of the reference, and then the real image and the virtual image. And because they are working slightly off axis, so we are assuming that the reference wave is slightly tilted and they have a phase that we need to introduce in order to apply the phase shifting techniques. But I can do it in the following way, right? So the intensities, I can say that those are one distribution, calling this at 0, and then I'm gonna have the another distribution, which is gonna be the object image, the real image and the virtual image, the 1, the 2, and each of them they're gonna have a different phase factor because the phase of the reference, right? So one is positive and the other one is gonna be negative. So this is how I'm gonna create. So if you look in this kind of new formula, in this new equation now, my hologram is the combination of 3 terms, the 0, the 1, and the 2, and the combination of them change based on the phase of the reference wave. So if I have 3 unknowns, I can use a linear equation system. So I need to have 3 holograms to get each unknown, the D0, the D1, and D2. And I'm just gonna create a matrix where the coefficients of the matrix are the values of the phase. So obviously for D0 it's always gonna be 1, but the other coefficients are gonna change of the values of the phase. So I'm gonna solve the problem using linear equations. And if I have exactly my system, if this is the hologram that I record, I can use the inverse of the matrix with the phase terms, so I can get my unknowns. Because at the end of the day, what I really want to get is this sub 1, because that's the object image. So the only thing that I really need to know is the phase terms, right? So let me explain how it works using a simulation. So I have this is not gonna be my true object. So I don't have any amplitude information. Everything, it's a phantom. Everything goes to the phase, and I create my hologram. And if we look the Fourier transform of the hologram for a particular value of the phase shift, I think it's 0. Then you're gonna say like the C term and then the D1 and D2 terms, and they don't have overlay, so they are working off axis. Right? So I just want to estimate the 0, the 1, and the 2 based on the 3 holograms that I'm gonna record it, and I'm gonna do it for different values of the phase. So the true phase values are 0, 60, and 180. And if I'm using the current phase shift, you're gonna see that when I'm doing the Fourier transform of these particular values, I get discrimination. I cannot get identification of one spectrum. So I'm able to decouple its properly. But if the phase shift that I'm using in the equation to solve the unknowns are different than the true values, you're gonna see that in the D+1 and D-1 term, instead of only isolating one single term, I have a combination of 2 terms, right? So based on this observation, that's what we are doing. We are kind of analyzing how many of the residual component appears on the true value. So this is what we're gonna create. So we're gonna create a const function that measures, like for example, if we are in the D+1, the center of the D+1 term is the real peak, and the center of the D-1 term are the residual, and we know the location of those ones from the hologram, right? So what I'm gonna do is I'm gonna get what is the amplitude peak for each of the values and get it as a const-function, and this const-function is gonna get through an iteration until it's minimum. So you're gonna see like, and this is the example, right? So the values really go into the numerical 0 value when the values are the correct ones, but the value of the const-function is definitely higher than 0 if it's different. And once we solve for when we minimize the const function, we don't only get the true values of the D+1 and D-1, we also get the phase shift. So when we have the phase shift, we can go back, use them, and get the estimated phase image. And you're gonna see here that the estimated phase image, the value that we have right there is the mean square error with the estimated phase and the true one, and really when the values are the correct one, the mean square error is 0. So that's what is gonna be the process. And obviously the simulation was working really well, but everything that you need to do needs to be tested experimentally. So this is the hologram that we are testing, and right here I think this is the hologram for a star target. So we have like 3 peaks right here. The system is slightly off-axis, but the D+1 and D-1 term, they overlay, so they don't need to be slightly off-axis without overlay. We might have some overlay with both of them, but from the hologram we know exactly what is the position of the peaks. We minimize the const function, so this are the Fourier transform of the D+1, the D0 and D-1. So you see like there is no peak on the position of the -1 term in the +1 term, and the same happens like there is no peak in the position of the +1 term in the D-1 term. So once you get the spectrum of your object image, the only thing that you need to do is like shift it back, you compensate that tiny interference angle and estimate the phase. And this is the reconstructed phase image where we did several radial profiles to kind of quantify the accuracy of the method for the frequency of the pattern, but also for the field of view to make sure that it agrees with the manufacturer value. So we tested with 3 images and it was working well, but really the object image and the virtual image, they have exactly the same information, right? So there is only a conjugation with them. So I can create, what I did was, I don't want to use 3 images, I want to even push the method a little more, so we're gonna only use 2 images. So now I'm creating a new image, which is this 3, which is gonna be a combination with a real image and the virtual image, where there is gonna be a phase shift with them. But that phase shift it's gonna be already estimated. And now my const function needs to be different. So instead of analyzing the spectrum of the new term, what I'm gonna analyze is the spectrum of the D0 term. And in the D0 term, if you go through the simulation, you're gonna realize that in the position of the -1, it appears like a residual value if the phase used is wrong, but does not appear any residual on the others when the estimated phase coincides with the true value. So this is now my new const function using only 2 images. Obviously, we use the same hologram, the same experimental images of the star target, and we compare them, what is the performance with 2 or 3 images, and we did like a quantitative profiles to kind of see the performance. So the performance is the same As you might see sometimes, like it looks like a little more noisy than 3 image, but roughly the performance is the same with 2 or 3 images.
Okay, coming back to the spatial filtering method to recover info from off-axis recordings, we need to recall that the desired info is the one of the +1 diffraction order or the -1 diffraction order in any case. First of all, to reconstruct the object information, it is necessary to filter out that +1 term by cropping its spectrum. After that, the angle of the reference plane should be compensated. To address this task, the crop part of the spectrum is centered on the new matrix by adding 0, 0 padding the image or the matrix. By Fourier transforming the new matrix, we obtain the object wave field at the sensor plane, that is the complex amplitude of the specimen. If the sensor is placed at the image plane, that is we have an image plane setup, then from the complex amplitude information, we can reconstruct either the amplitude and the phase contrast image of the specimen. But of course, it is not an easy task. We need to pay particular attention to the reference compensation step. This step is particularly important to provide phase contrast images without any distortion, that is, like images like this one. This is important mainly because we are interested in using the phase value for accurate measurement for instance, topography of the sample or refraction index measurements. So to do this, we need a fully compensated image. Quite frequently, and in microscopy in particular, it is easier to compensate the reference waveform in the space domain. So from the crop spectrum of the hologram, we apply its inverse Fourier transform, and the resulting complex distribution is then multiplied by a digital reference wave. This digital reference wave, the one that is numerically produced, should be a reply of the same physical reference wave used to record the hologram. So the angle of the reference waveform is determined by the wavelength of the light source and also by some parameters of the camera, such as the number of pixels, the pixel pitch. Then the subtraction between the pixel position of the DC term and the +1 diffraction terms give us the proper information. So the DC terms is always placed at the center of the Fourier spectrum. Therefore, the only parameter that needs to be known is the position of the maximum peaks of intensity in the +1 diffraction order, that is this one over here. We call this position U max and V max in the next slides. Theoretically, if the reference waveform is a plane waveform, as we assume in the experimental setup, then the values of U max and V max can be determined by estimating the position of the maximum value within the +1 diffraction order. If this determination is accurately done, then the complex distribution scattered by the sample is then the multiplication between the inverse Fourier transform of the filter hologram and the numerically modeled digital reference wave. And as we already know, the phase man is hence obtained by applying the inverse tangent function to the complex distribution information. So, as I already mentioned, the only parameter to be accurately estimated is the interfering angles, which is obtained by the accurate determination of the position of the maximum peaks of intensity in the post-1 diffraction terms. That is this one and this one over here. But this is important. If the frequency of the plane reference waveform coincides with the integer pixel position, which is very challenging in a microscopy setup, the value of Umax and Vmax can be determined by estimating the position of the maximum value and the +1 diffraction term. But yeah, as you all can suspect, experimentally this condition may not be always be satisfied due to the discretization of the continuous complex distribution provided by the sensor. Each nanometer change can make the things blow up. So the most common experimental scenario is where the maximum peak, the maximum point, is not accurately represented by the pixel-wise distribution information. So we will probably need sub-pixel precision to accurately compensate the face image, so we cannot obtain information like this one on the right. We see that there are some phase jumps due to the improper non-optical reconstructed face image. But we need this one. So to achieve this one, we need a proper estimation of this of the position of the +1 peak maximum intensity peak. Okay, a couple years ago, we demonstrated that the best reconstructed phase map is the one which has the less phase perturbation. That is the smallest number of phase jumps. So to provide that information, we implemented a metric that accounts for the numbers of phase jumps present in an image. When we tested over a whole big number of or large number of images, well, we only needed to see when this number happened to be the smallest. So there is a need to find the optimal non-integer discrete position of the maximum of the +1 diffraction order. Professor He and his group proposed the use of a center-based algorithm. They use thresholding applied to the Fourier transform of the hologram around and being interested in a window surrounding the +1 diffraction order to automatically select this order and then to determine the center of the filter algorithm. Nonetheless, this approach could lead to inaccurate measurements if there is some errors in the estimation of the centers. So the estimation of the center is critical. So to solve these problems, we started developing iterative methods based on nested loops, essentially, in which we determine the brightest point of the inside the +1 diffraction order, and around it we determine a grid, a bunch of points inside or around this point, and we calculated the metric to determine whether phase jumps are obtained or not. And to do this, we just needed to apply this over different reference, synthetic reference. We applied them on the hologram. We obtained the phase map. For each phase map, we measured the number of phase jumps, and we determined that the proper phase compensated images, as I mentioned in a couple of slides earlier, well, is the one with the least number of phase jumps. This method has been applied in using the centroid tool in an efficient method, or an efficient version of the original method, but essentially the idea is that one. We apply the method, the measurement of the phase jumps for reference built from a grid of points around the +1 diffraction order. In this case, we make the method more robust because we are not only using the +1 diffraction order, we are using all its neighboring points in a sub-pixel fashion, of course.
So my colleague has already explained to you some automatic methods where there is like a smart search of the position of the interference angle. So I'm gonna introduce to you another different type of search. So the search that I'm gonna talk to you is about minimizing a cost function, and Carlos was already telling you that the best reconstructed face images for thin objects that they don't present wrapping of the face is the one that they have the minimum values of phase jumps, right? So here you have like a face image where there are like phase jumps, meaning that the interference angle has not been set up properly, or this one where we really have like we have some phase jump at the edges, but pretty much the background of the image is uniform. So those kind of, every time that you have a cost function, there are already automatic algorithms that minimize them, and they are really robust. So the method that we were using before were kind of counting the number of phase jumps, right? And kind of like, and we need to minimize. So we know like the whole image, somehow we are creating a binarized image for the reconstructed phase image. Ideally, all the pixels, if we binarize the image, the whole pixels needs to be white, right? So the total number of pixels are gonna be the number of pixels, the product of the number of pixels that you have in the horizontal and vertical axis. But what we're gonna do is we're gonna count how many pixels are gonna get kind of black. So that's what we're gonna do it. Like if the image is perfectly pixelarized, then this kind of sum is gonna give us an N. So the J is equal to 0, but that's not gonna happen. We're gonna have always some phase gaps in the edges. So we just need to kind of minimize our cost function. I'm just gonna change a little the discussion here, and we're gonna talk about how affect the optical configuration on the accuracy of your face image. So this is the most conventional and most general DHM system, a mass sender interferometer, where now the sensor does not necessarily need to be in the image plane of the microscope, and where the distance between the aperture stop and the tube length is arbitrary. So that means that you are illuminating the object with a plane wave, but after the tube length you have a spherical phase factor. Alright, so the complex amplitude distribution scattered by the sample at the sensor plane is the 2D convolution of the complex amplitude distribution found at the image plane, convolved with the free space propagator by a distance c. And c can be positive or negative depending if you are in a plane before the image plane or after the image plane. And the complex amplitude distribution at the image plane is in general proportional to a quadratic phase factor, where c depends on the optical configuration. So it's kind of like it's the radius of curvature of a spherical phase factor, where it depends on the distance d, and then that's gonna get multiplied by the 2D convolution of the scale version of the object information, convolved with the Fourier transform of a scale version of the Fourier transform of your pupil. And if we are in the telecentric DHM system, what is going to happen is that this quadratic phase factor go away, because c now is going to become infinity, so 1 divided infinity, that's going to be 0. So you illuminate with the object plane and a plane wave, so the phase term is not distorted by any spherical phase factor. So let me show you. And in that particular case, we say that the system is shift invariant from the optical point of view. But if the distance is different than the focal length of the objective lens, then now we're going to have a quadratic phase factor that needs to be compensated. And depending on the position of the object, you might have, it's going to get distorted differently by the spherical phase factor. So let me show you what is going to happen. So you have the hologram, right? And the hologram is recorded in a fax in non-telecentric regime, and it's hard to see that from the hologram point of view. Like if you make a lot of zoom and you kind of see the fringes, you might say that the period of the fringes is not the same, but it's really hard to see with the eye. But if you go to the Fourier domain, it's super easy to identify telecentric versus non-telecentric DHM systems, and the only thing that you need to see is the size of the d+1 and -1 term. So if they are non-telecentric, they're gonna have this kind of like rectangle shape. So what is gonna happen is that the spectrum of the +1 and -1 term, instead of being enclosed in a circle, they're gonna go kind of enclosed by a rectangle. That is, the size of the rectangle changes with the radius of curvature. It's inversely proportional to the radius of curvature of the quadratic phase factor. So let's assume that we cannot binarize my spectrum, because I want to know what is the size of my quadratic phase factor. And if I have the size, then I can definitely filter out my +1 term, but I can also kind of see the radius of curvature, because it's kind of equation, and I know that the reference wave it's kind of like in the middle. The interference angle is going to be this middle term of the d+1 term. So I can compensate by so I filter it out the +1 term. I compensate by my inverse Fourier transform, and then I do the inverse Fourier transform, and this is the phase image that I get. So you see here the spherical phase factor going to the phase term, so you don't really see the object information, you just see the strong spherical phase factor distorted. So that spherical phase factor needs to be removed, and I'm gonna talk to you how to do it. So there are different methods. One method is do a polynomial fitting to kind of create like a conjugated spherical phase factor from that image, but I'm gonna talk to you about the method introduced by Min, and that was the Kemper group. So what they did here is like, alright, so I can estimate, I know what is the relationship of the radius of curvature based on the size of the +1 term, but I know that I might have a mistake centering the reference wave, and I know exactly where is the center of the reference. Like, you can't really do right now like the filtering of the +1 term, and this is like the position of the spherical phase factor. So now what I can do is I can create a conjugated spherical phase factor to compensate this phase image and get a fully compensated phase image like this. So I just do it like the spherical phase compensation to have at the end one fully compensated phase image.
So up to now, we have discussed how to process DHM holograms that are acquired in an image plane setup. But what happens when the object does not fulfill this condition, or the camera does not fulfill this condition? Well, we need to propagate. We need to numerically propagate the wave field to obtain a truly in-focus image. So to do this, in DHM in particular, a discrete version of the angular spectral propagation is good enough to do the job. And in this case, as you all remember, the angular spectrum takes the information of the complex amplitude in the space domain, it takes it to the frequency domain, and in the frequency domain, it applies the kernel of the propagation as it is determined considering the distance of the propagation. In this equation, that would be the z letter. And after that, we come back to the domain, to the space domain, to obtain information of the sample. It is well known in digital holography that different metrics to autofocus the holograms have been proposed, and we are not changing this in DHM. In DHM, what we have is a different set of reconstruction in different propagation distance, and the image with the highest value of the metric for the autofocus metric is the one that yields to completely in-focus images. We can do this in amplitude, and then knowing the proper distance of the DHM hologram, reconstruction of course, well, we recover the information in phase, and then we have a proper phase fully compensated, but also fully in focus image of the sample, as we can see here. So finally, to summarize, in this talk, we addressed the first, how to identify the proper numerical reconstruction method for particular DHM's configuration. We also studied some different methods to recover information for 2, 3, and 4 phase shifted hologram, both in inline setup, a slightly fast axis setup, and also in situations in which the phase shift is not known, that is in blind methods. Also, we realized the need for phase compensation algorithms to recover information in off-axis DHH hologram by doing this spatial filtering procedure plus the digitally reference compensation method. And finally, we appropriate the numerical methods to recover information for holograms capturing non-telecentric, and of course with the sample out of the image plane of the system. And of course, we would like to acknowledge our collaborators all around the world, in Colombia, in Spain, and in Belgium, in the US. They make our work more impactful. Also, to be able to do our research, we received some funding from the University of Memphis, of course, the Universidad de AFID in Colombia, the National Science Foundation, the Ministry of Science in Colombia. And we would like to also acknowledge the different people in our research group, both from Anna's labs and from my lab. And that's it. I hope you have enjoyed this talk, and we see you in the next delivery. See you.